This video goes into how to find the representation of a function using power series, and then a couple applications of doing so. So how do we find then a function's power series expansion at C? Well, a good way to do it is just to use a known convergence series and what that series equals, and then using series operations to find a series representation for your function. If you're really desperate, you could always just use the definition of a Taylor series in order to find, let's say, the first 4 or 5 terms of the power series, if you're not worried about convergence. And just remember that a function, if it has a power series centered at A, its coefficients are uniquely defined by that function and its derivatives evaluated at A. So it doesn't really matter what method you use to get the power series. You will always get the same thing, provided that the function has a power series expansion. So just to remind you again, here is a list of Taylor series that we know converge and that they converge to the original function. A lot of these I have already memorized, or I know how to go about getting them. The sine, the cosine, e to the x, and the binomial series and the geometric series are all ones that I just know and I just use whenever I need them. Anything else here you actually can just derive on your own. You won't have to be memorizing any of these, but if you really want to spend some time, if you want to memorize anything, I'd memorize those 5. The sine, the cosine, e to the x, 1 over 1 minus x, and 1 plus x to the kth power. Those power series pop up enough that you might want to just know them. One of the most common ways to find a power series for a function is to use a power series that you already know it converges to a certain function and just replace x on both sides with some continuous function. By doing so, the new power series also converges as long as the range of the function in absolute value lies within the interval convergence of the original power series. So the most common uses here is just to replace the x on both sides with, let's say, a constant times x, or x to some fixed power, or x minus c, or just to multiply the function by just some simple polynomial. Some other tricks, we can use algebra. Since they're just power series, we can add them, subtract them, divide them, and we'll get power series. And the nice thing is, you just treat them like polynomials and you're fine. So you can add 2 power series to get a new power series. You can multiply 2 power series. You can divide 2 power series. And the way you do multiplication or division, typically you only actually do these, the multiplication or the division, to go and get, let's say, the first 4 or 5 terms of the resulting power series. And the way you do it is just like you normally do with any 2 polynomials. You FOIL them, or you do a kind of long division. Also, if you have a function that's defined by a power series, you can get another function, being its derivative or its integration, just by doing term-by-term integration or differentiation of the power series. And the neat thing is the radius of convergence doesn't even change. Now, of course, the interval convergence might, but the radius of convergence doesn't. This allows us to find new power series by using integration or derivatives. So let's go ahead and try this a few times. One good example is trying to match a function, especially something like a fraction, and matching it to look like the geometric series, and then just using that to get the answer. So see, if you see the function 3 over 2 plus x, notice you can rewrite that as instead 3 over 2 divided by 1 plus x over 2. And you can write that as 3 over 2, 3 halves, divided by 1 minus a negative x over 2. Well, that means then I have written this that way, where the a is 3 halves and the x is negative x over 2. So this has a power series expansion, and its power series expansion is 3 halves times negative x over 2 to the nth power, as n goes from 0 to infinity. And even better, I know when the geometric series converges. It converges when the r is less than 1 in absolute value. So that series will converge to 3 over 2 plus x as long as the r is less than 1. And that means as long as the absolute value of x is less than 2, this series is going to give you that function. So you can always, if you want to, I could approximate this function by using a partial sum of this infinite series. So let's use these 2 series. 1 over 1 minus x is 1 plus x squared and so on. And then from that, I could replace the x in here with negative x, and I just do that on both sides. That would then give me a power series for 1 over 1 plus x, which is 1 minus x plus x squared minus x cubed, and so on. And I've written down the formulas for you. So because of that, I can then find a formula for this guy's power series, because this is 1/2 the subtraction of these two functions. So that should then be 1/2. And in order to add or subtract polynomials, you just add like terms like always. So here, take this guy, subtract that guy, that'd be 0. Take this guy, subtract that guy, that's 2x. Take this guy to subtract that guy, that's nothing. Take this guy, x cubed, and subtract a negative x cubed. That would then be plus 2x cubed. I think you can then see that the next one should be 2x to the 5th, and so on forever. But the 1/2 then would distribute through. You would then get x plus x cubed plus x to the 5th, and so on. You could write that as it's a series as n goes from 0 to infinity of x. It's 2n plus 1. That's it. That's the power series for that function, x over 1 minus x squared. And it's got to converge in the intersection of the two separate intervals of convergence. So this thing will converge at least as long as the absolute value of x is less than 1. That's it. That's how that problem would be done. To emphasize that if a function has a power series, there's only one, I'm going to find the power series for 1 over 1 minus x quantity squared 3 different ways. So the first 2 ways won't actually give me the formula for the series, but it will give me the first few terms of it. Notice that 1 over 1 minus x squared is actually the same as saying 1 over 1 minus x, that whole function squared. But I have a power series for 1 over 1 minus x. So think of this as a product of 2 power series. So just multiply this out like you always would. Just distribute all the way through. Multiply the 1 throughout the entire terms. So if you take 1 times 1, you'll get 1. Now look for all products where you can get an x. You get 1 times x. You can get x times 1. That would be x plus x. Look for all the x squares. You can get 1 times x squared. You can get x times x. You can get x squared times 1. That would be x squared plus x squared plus x squared. And similarly for the x cubes. So simplifying that, you should get this. That should be the power series. That should be the power series for 1 over 1 minus x squared. I've only written out, though, the first 4 terms of that power series. Although by looking at it, you can probably guess at a general formula. Now I've also graphed the function 1 over 1 minus x squared, and I've graphed the Taylor polynomial up to order 3. So you can see that as long as you're near 0, the graphs are pretty similar. It's only when you get away from that that they start to diverge. Let's do the same thing, but this time let's do a clever use of division to get the answer. So 1 over 1 minus x squared, that's really 1 divided by the polynomial 1 minus 2x plus x squared. Think of it as you're dividing 2 power series, and do long division, but go from least degree to highest degree, not highest degree to least. So I would set the long division up this way. Then think 1 goes into 1, that goes 1 time, multiply your 1 times your divisor, get the resulting product, now subtract terms. That's what's left over. Repeat. Take the 1, the leading term in your polynomial in least to greatest degree order, divide that 1 into the 2x. That goes 2x times. Take 2x times your divisor, multiply it out, subtract. You then get that. Then take the 1 into the 3x squared. That goes 3x squared times. And then just keep going as far as you want. Notice I went up to however many terms I was interested in. That's 1 plus 2x plus 3x squared. That's what I got moments ago. That's the exact same thing, at least the first 3 terms, when I use the multiplication technique. This time, though, I'll write down a formula for it so you can see. That is the actual formula, which if you wanted to, you can prove by induction. But you can't really get that by using the division or the multiplication trick. One last time. Let's use the series 1 over 1 minus x being equal to 1 plus x squared and so on. That's the geometric series. And use differentiation to find the series for 1 over 1 minus x squared. Because I noticed that that function, 1 over the quantity 1 minus x squared, That's just the derivative of 1 over 1 minus x. So then just take the derivative of all those terms in the power series, because that's how you do derivatives for power series. So taking the derivative of the overall formula gives you that. And notice, if you want to, you could replace the power on x with k by re-indexing. So k is n minus 1. That means then n would be k plus 1, and you get this particular series. As k goes from 1 to infinity of k plus 1 times x to the k. And that's exactly the same thing we had moments ago. That's just a different way to do it. It's this flexibility that it doesn't really matter how you find the power series. In the end, you get the same answer. That frees us to do all kinds of neat applications. So for example, what if I wanted to find the integration from 0 to 1/2 of the arctangent of x over x? Now instantly, this is an improper integral, because notice that the denominator x would be 0 over the interval 0 to 1/2. So then you can't do this nicely. We'd have to do a limit process. Also, finding the antiderivative of the arctangent of x over x is really hard. But think of it in terms of x is between those numbers, and replace the arctangent with its power series. You then have 1 over x times that power series. Now, as long as x isn't 0, that's totally fine. But then I can take the 1 over x and just multiply it through. That would then decrease the power on the x from 2n plus 1 to only 2n. But then I have the integration of a power series. I know how to do that. You just integrate each term bit by bit. So I increase the power by 1. So it's 2n plus 1, and I divide by that power. So the denominator now is 2n plus 1 squared. And then I evaluate this from 0 to 1/2. Again, really the 0 here, that should be in the limit as x approaches 0. But if you just plug in a half, you get a series of -1 to the n times 1/2 to the 2n plus 1 over 2n plus 1 squared. And if you plug in 0, all the powers on x are at least 1. So if you plug in 0, they all vanish anyway. That's the answer. That's the exact answer as far as what that integral equals. Now that may not be satisfying. You might look at it and go, yeah, but what does that sum equal? Well, it equals something. It converges to something. But if you want to approximate it, here is the sum if you write out the first few terms. Do you see how it alternates? So since it alternates, I can stop anywhere, and the error in the estimation for that partial sum is less than the absolute value of the next term. So for example, if I add up only these first 3 terms, then that's what the integral equals, and the error is less than that number. So the approximation is pretty darn good. Another sneaky use of power series is to actually find the exact value of sums. Notice that this particular sum, you could write it instead as 2 times the summation as n goes from 1 to infinity of 2 to the n over n factorial. But we know though that the summation as n goes from 0 to infinity of x to the n all over n factorial, that's actually e to the x. So if I look at the summation as n goes from 1 to infinity of x to the n over n factorial, that would be the overall summation as n goes from 0 to infinity of x to the n over n factorial minus the one term I don't want to count here. The only term I don't want to count here is when n is 0. So if I plug in n to 0, you would get 1 over 1, that's 1. So this is then e to the x minus 1. So I now know what this thing equals. Well, this summation is just this power series evaluated too. So then this has to equal 2 times, and that would be this function evaluated too. That is the exact value of that summation.